Thank you, Evan, for organizing the meeting today too. But folks, I'd like to begin by saying that I am not a scientist. I am a historian. I happen to run an invention company. So, but ultimately, and I'll say this too, that I'm an environmentalist. I'm sure all of us are. But the concept of blending a historical perspective with environmentalism is what I'd like to introduce today as a sort of a needful direction for all of us, in that there are a series of, as we all know, a series of extinction events that have happened in the past. And it appears that we're at the cusp of another one right now. We're describing our efforts around climate action as a way to mitigate climate change, when in fact, I think it's important that we name the problem, which is the extinction event that will ensue in the event we don't succeed. And it's upon us. I don't want to dive into, I don't want to take up too much of our time around that point, but let me say this, that the great Permian extinction, in which over the course of 300,000 years, 96% of species went away, we're achieving numbers comparable to what happened then at a dramatically higher rate, a faster time period. We don't have as much time. We don't have 300,000 years by any means. But test those numbers out, do some math. I invite all of you to do that instead of hearing from me, a historian who will likely bumble the numbers. But bottom line, the reality here is that we're in a unique place in terms of having a window of opportunity to make a huge difference in terms of the survival of mankind. I hope it doesn't sound too grandiose. The work that we're doing around a form of methane, biogenic methane, is, from my perspective, it represents the us working on what I would describe as the bullet. If we look at an analogy, it would go something like this. Carbon dioxide is a trigger event. As it occurs, it can dramatically expand the second phenomenon that occurs when carbon dioxide happens. A little bit of climate change, and all of a sudden you get a phenomenon occurring in fresh water associated with bioslime, with phytoplankton blooms, cyanobacteria, blue-green algae. That represents essentially the, if carbon dioxide is a trigger, this is essentially the powder, if you will, because when those events happen, that phytoplankton occurs, you ultimately get the other biogases occurring. The methane takes place after that as water becomes anoxic and anaerobic in a big way. Back in 1971, approximately 50% of waterways in the US were eutrophic. I'm sorry, 15% in the early 1970s were eutrophic. Now we're at 51%. The difference between a eutrophic waterway in terms of methane emissions and an oligotrophic waterway, a nutrient poor waterway, cleanest water, is the difference between 150 ppm and 2000 ppm per unit. But the ratio of eutrophic water that we're contending with is something that my business, Floating Island International, that's really what we're taking on. We're finding ways to cycle nutrients up and into and through the food web instead of letting them ultimately get transition into blue-green algae, or harmful algae blooms. So this incidence of harmful algae blooms is a parameter that we can look at to develop a perspective around what's going on in the form of nutrients and their cycling into ultimately methane coming off of impaired water. There's a paper out of Yale. Dr. Judith Rosentreter was one of the authors, but that paper identified that essentially the methane coming off of nutrient-impaired water, off of fresh water here in the U.S. is approximately 40% more in volume than is coming off of oil and gas, all oil and gas. So the relative volume of methane that we're dealing with associated with this phenomenon, a little bit of climate change, the warmth effect that results in harmful algae blooms, resulting methane, is something that we need to address. We don't have a lot of time. We need to get on it. We're spending a lot of time thinking about other forms of greenhouse gas, but this one, the researchers like Dr. Del Santro or Judith Rosentreter, or the paper that Andy's going to pull up in just a little bit here, will reflect that very point. So, Andy, would you like to pull up the paper that'll kind of guide us through the conversation?
We should have the paper up, and I put it actually on the amount of contribution that comes from the various types of eutrophic versus a clean water versus nutrient impaired water. And this is the huge difference in terms of the area from 50 milligrams for a clean water system to a eutrophic system at 8,000 milligrams of carbon per square meter per day. Okay, and then we were gonna, as a basis of the discussion is.
Okay, I'll step in here, Andy, to say that the hypolimnion area in reservoirs is typically where today under eutrophic conditions, that's where your deficit of dissolved oxygen will occur first. And methanotrophic activity, methanogen activity occurs not in the water, but in the sludge underneath that zone. And essentially methane, if there are no methanotrophs to consume it, will ebulliate up and through that hypolimnion area, and then forward up from there into the epilimnion, but ultimately into the atmosphere. Or if you're a reservoir, if the reservoir is pulling from the hypolimnion, which many do, then you ultimately will experience the concentrated greenhouse gas phenomenon, the methane, not to mention hydrogen sulfide and a number of other gases will be coming out of the turbines and will quickly ultimately enter the atmosphere downstream from the reservoir. The goal, the vision for fixing this phenomenon, long range, would be to prevent eutrophication. But that, as we all know, is an onerous task. Limiting agriculture, which is responsible for about 80% of the nutrients that occur here in North America, at least, and that get in the water, isn't something that's going to happen tomorrow. On the other hand, the potential to oxygenate into the sediment, into the sludge, and to sustain and maintain a population of methanotrophs, that may very well be a far more practical approach to this issue. Andy, do you want to step in here and enter your thoughts?
Okay, we're dealing with what's called allocanthus input, which is the carbon that comes from the river from sediment runoff and particulate organic carbon. That's considered what's causing the eutrophication. Then you have what's called the autoconthus, which is the sedimentation that's coming from algae and stuff like that as it forms and degrades. And so the higher algae sedimentation rates you have, more algae in the water, then you're going to have a higher level of methane in the eutrophic waterway. And so what we're trying to do here is that these emissions that you're looking at, the ebullition emissions, and Tonya has actually described that the size of the bubbles, as you get a really deep reservoir, those methanes, when they bubble up, they actually dissolve in the water. And if it's more than 60 meters deep, then it actually dissolves. And that's part of this paper. So we're seeing the effect of the methane being absorbed into the water, and most of it accumulates in that bottom layer. The concentration of methane is highest right where it's being generated, and it's really just a diffusive transfer upwards to the upper layer. And then you actually see the methane oxidation. The only way that methane can be removed is you can actually have the methanotrophs, the methane breakdown when you have oxygen present. And so if we can increase that methane layer, which what's Bruce doing, we can get it all the way down to the sediment. And it's kind of analogous to what happens if you look at the sediment type in a really deep part of the lake versus in the shallow part of the lake. The sedimentation looks a lot different in the shallow part because it's decomposing with the resource of oxygen. And you can actually look at a lake and see at the edge that it's not producing as much methane as it does. It does get absorbed into plants, and they're looking at major source of methane is that sediment decomposing. And so we're proposing a process to oxygenate the lowest layer of the water, and coming up with system designs that'll help do that in order to get methanotrophs to survive and then absorb the methane. And in theory, if we can reduce the methane concentrations right near the sediment, you'll also reduce ebullition as well. Again, that's a theory, but so that's kind of a summary here. Primary and the majority of emissions in reservoirs, reservoir depth is really critical. If they're sampling from the epilimium to run their turbines, which is the upper layer of the water, it's warmer water, you'll actually have less methane being produced by that reservoir. But the majority of dam construction and reservoirs is producing from that cold water, and that cold water that's coming out actually contains all that higher concentration methane because it's much higher concentration at that lowest layer. It's going into the rivers down below, and that's where the methane emissions occur. It's actually it does have typically it's oxygenated water, and it's a diffusive process, but it's very shallow. And so the majority of the reservoir emissions from deep turbine, deep outlets is downstream from the dam. You're not going to find the emission at the dam. It's in the waterway just below it.
Yeah, in fact, Andy, I'll note that there are a number of different ways to quantify how much methane is coming off of a reservoir. And as Andy points out, especially based on where the turbines are, most again occur towards the bottom of the dam and pull from that anoxic or even anaerobic water in the bottom. An example would be a Bureau of Reclamation reservoir near here that's 430 feet deep, just above the dam. And it's eutrophic. And the reality is that the volume of anoxic and anaerobic water that occurs above, in that setting is incredible. It's really huge. However, if we only have to oxygenate into the bottom of these eutrophic waterways, into that stratified cooler water, we don't have to treat the entire reservoir. Again, because when you get up into that epilimium, you're essentially dealing with a location where the oxygen typically is still there. There's still DO occurring, unless it's truly a dead zone of a water body, which that happens too, but not very frequently, fortunately. But you're looking at about 85% more methane coming off of the anoxic anaerobic zone than you're going to find in the upper epilinian zone. And that's the secret to, let me call it, describe it as that's the direction that various technology options are developing today. There's it's called oxygen saturation technology, and there's a company launching out of Madison, Madison, Wisconsin, that's taking that one on. Here at Floating Island International, we use an airlift technology to pull water up from the bottom, add oxygen, and send it back to the bottom without changing its temperature. On that basis, we only have to treat the stratified bottom layer of the water body. We don't have to treat the entire water body. Same thing with that oxygen saturation technology. They're developing a means by which to add a concentrated version or form of oxygen, I should say, and then put the water back, and doing all that from grid-based shore-mounted systems. Here at Floating Island International, we're designing, I should say, around doing what I described. In other words, the airlift system to oxygenate the water and put it back without changing its temperature. But we're doing that on solar platforms so we can operate off grid. What I'm describing is early stage. There's another technology called total lake aeration, a company out of Michigan called Everblue, headed up by John Tucci. But John has been at this for a couple of decades now, but ultimately they put in a grid system of air diffusers across the entire or major portion of the lake, and can treat the entire lake that way. Expensive, and probably only most suitable in a relatively shallow setting, but still it works. And John has a history of performance. So I'm sharing all this with you because the bottom line is that I'm noticing that there's a wealth of incredibly salient, important research unfolding today around this major source of methane, but we need to take it to the next level. We need to get at it in terms of addressing it, because it represents it's the very same driver that caused the great Permian extinction. The only difference is it's happening today, and it's happening now at a much faster rate. So with all that being said, I guess, Andy, can you think of any key points here that we should make that we haven't already addressed?
I'm thinking here, that's a great question, Bruce. I think how methane moves through a reservoir system is, the fact is, we talked about stratification as being really important in terms of a lake. My studies in looking at how water temperature profiles and stratifies, it's such a powerful effect. People can't realize, if you ever swim in a lake and you feel that upper layers that you're swimming in, and you put your feet down, you can feel it's so cold down below. It's amazing how lakes do stratify. You don't want to destroy that. And if you're using diffusers to aerate a lake, you actually will de-stratify the lake. And then that takes the warm water, and then it makes it overall the bottom layer the warmest, the sediment becomes warmer. And this paper actually talks about small changes in a parameter and what is the effect on theoretical emission rates. And this is a really important part of the paper. I thought near the end they were going through that, and they were showing how this modeling, how it's working from eutrophic lakes to the upper part of this graph to highly non-eutrophic. We could just spend our time and discuss and go through this paper, but these kind of data here is the factors affecting carbon input, factors affecting methanogenesis. The fact is that temperature is so important. So if you're using a typical aeration system, you destratify the lake, you warm the sediments, and you increase the degradation rate of the carbons and increase methanogenesis. You do get the oxidative effects that are working, but which are listed as being reported in here. And I think that this is, all of this goes back together is the most important way to oxygenate the water is to not destratify it. And when you looked at that computer model, this is a theory on my part, but it's actually kind of confirmed, is that you get density gradient flows. And so all the methane that's being generated in the shallower upper portions of the water as it's traveling, it's going to be cooled by the cooler sediments. Sediments are always cooler than the water themselves. And as it travels down, it'll be cooling and it'll end up in the deepest spot in the lake. And so that from a process of treatment, you can do a hot spot and actually have a big bang for your buck if you treat that area just prior to the dam or in the deepest spot of a lake, is a way to come up with a way to oxygenate those lower layers and then treat it. And so that's kind of the philosophy, is the you treat hot spots and you don't have to treat the entire lake. You can cause a significant reduction in that methane being generated.
Yeah, Andy, and in fact, I could insert here that, for example, the reservoir I mentioned earlier, Bighorn Lake above it stretches across from Wyoming into Montana, but it's a long extended waterway. And we've identified, after reviewing what's its actual profile, that 3 or 4 of the treatment zones would mitigate a huge volume of the total methane. So the potential practicality of taking on waterways like that. And in fact, there's another data point that we used the formula from the Yale paper to extrapolate, but the 3rd largest reservoir here in Montana is called Canyon Ferry, and based on the emission calculation formula presented in the Yale paper, it is generating currently about 10,300 tons per year of methane. So the irony of all this, what still my mind is swimming in reference to this point, but it very much looks like the U.S. government is the single largest emitter of methane happening in the country today. And the U.S. government, the Bureau of Reclamation, or the Army Corps of Engineers, actually Army Corps of Engineers controls the most water in reservoirs here in the U.S., followed by Bureau of Reclamation. But yes, there are other considerations or other problems that need to be dealt with relative to climate action. However, what's unique about this form of methane is that the biggest part of the work will involve the U.S. government actually addressing it. And so far, it's not happening. So the researchers that are out there that are working on this are beginning to get the attention of national governments. And here in the West, where the primary form of carbon is coming from from essentially plant material, autotrophic forms, versus the carbon associated with erosion, perhaps organic sources, being the single largest, the largest source of carbon that occurs in tropical settings, Africa, India, places like this. But the reality is that we are in a wonderful place to be able to demonstrate an ability to actually mitigate massive volumes of this incredibly potent greenhouse gas. I'll mention as sort of an interesting corroborative data point. But NOAA has been tracking the difference between methane or the different concentrations of methane at their 50 different tracking stations around the world. These tracking stations are located in places where they're far removed from any single point source emission. They're trying to establish baseline, but they're with carbon dating able to identify when they're measuring methane that comes off of oil and gas versus methane that comes from biogenic sources. And the methane coming off of oil and gas is relatively stable now. The methane coming off of biogenic sources is expanding. And based on in my work, what I know about water and nutrient impairment and all of that, I can see that there's absolutely no doubt that this incredibly large source of methane is about water, about nutrient impaired water. That's the window of opportunity, if you will, for us to really target and get focused and make a significant difference in terms of our atmosphere. I'm at a point here, Evan, where I'd be. I think we presented sort of an overview of what we're doing and where we are, and I'd be very pleased to respond to any questions.